Hi everyone. Today we are going to be learning about phase changes and how they can be described as either exothermic or endothermic. What are the differences between these changes, and then how can we differentiate some commonly misused terms like evaporation and boiling. So before we start doing anything, what we want to do is identify what these phase changes are. So keep in mind that phase changes are breaking IMFs. So this means no new chemicals are made. So any material, any compound, any element, anything in the universe that is matter can exist as a gas or a liquid or a solid, all just depending on the right conditions. So when a solid turns into a liquid, we call this melting. So hopefully you knew that. And when a liquid then turns into a gas, we call that vaporization, which sometimes we'll see the term boiling being used. Then the opposite of that, if we're going a gas into a liquid, that is known as condensation. And a liquid then turning into a solid is freezing. That's kind of the term that we use for it. But freezing sometimes gets this connotation that it means it's cold. Things can turn into a solid and freeze at extremely high temperatures. So try not to get too caught up on that. So sometimes we'll use the term fusion. And then there are very few instances where I can sort of skip that middle liquid phase. I can go from a solid directly to a gas through a process, what is known as sublimation. And I can go from a gas directly into a solid, and this is known as deposition. Okay, so all of these state changes you need to know. So you need to know like this whole thing that I just drew on here. You have to know which direction the arrows go, and basically all the different ways that matter can exist and change in these different phases. So what's the difference then between an exothermic and an endothermic? So an endothermic is something that requires heat. So energy from outside of the system goes into that material. So what that means is as it's absorbing energy, what you feel as a result is cold. So something that is endothermically reacting, or what's called an endothermic reaction, is going to be absorbing heat, and that to you feels cold. The opposite then is an exothermic reaction where energy is being released into the surrounding environment, so you feel that as heat. So if we think about these phase changes, things that are exothermic, where the heat is leaving the system, right? So when heat is leaving, things are cooling down. That would be condensation. That would be deposition. That would be fusion, or what is called freezing. So these are things that are releasing heat in order to change their state of matter. The opposite then is where heat is absorbed. So that would be something like melting, or we might see sublimation, or we might see vaporization. So this is where heat is being absorbed in order to do this next step. So I can't melt something unless I absorb heat. So if I want to melt ice, the ice has to absorb heat from somewhere. That's going to be from the surroundings. So in an endothermic, the heat is absorbed. So just keep that in mind. So this is a very tricky looking graph, but this is what is known as a phase diagram. So in a phase diagram, you have two different axes that are plotted here, pressure and temperature. So for any material, it can exist as a solid or a liquid or a gas, just depending on what the pressure and temperature are. So that can change as we modify the pressure and modify the temperature. So the pressure is increasing. Oops, I wanted that to be a pencil. The pressure is increasing as we go up, and the temperature is increasing as we go up. So you think about something that's really low temperature, maybe something that's really low temperature down here, like close to absolute zero. It's going to be existing pretty much as a solid at that temperature, okay? If we were to increase the temperature to maybe, let's say, somewhere like here-ish, it could exist as a gas or a liquid, just depending on what the pressure is in that situation. So I'm going to show you some more details with how you read these and how these diagrams work. So this is an example of a phase diagram for water. So water is very useful for us to study because we have certain values for water. So I know the melting point of water is always going to be 0 degrees Celsius. The boiling point of water is going to be 100 degrees Celsius, but these are both at 1 atmosphere of pressure. So what that means is if I go somewhere that has a different air pressure, somewhere like Denver, Colorado, my boiling point is going to be a little bit different. So that's why if you've ever seen on cooking instructions, it might say if you live at higher elevations, change how it was you were going to cook this material, maybe boil it for longer or whatever else, and it has to do with those melting and boiling points being adjusted. So there are two kind of things to keep in mind, what's called a critical point and what's called a triple point. So these are hard to get to. They really don't exist very often in nature, but sometimes we can get ourselves there. So the critical point is where I can't distinguish between the liquid and gaseous states, as in the molecules are at such high pressure and such high temperature that I cannot tell the difference between one or the other. Typically at any other pressure or temperature, I would be able to distinguish between a liquid or a gas. But in that critical point, that exact pressure and temperature, that's not going to be the case. And then the triple point is a very specific temperature and pressure where all three states of matter are happening at the same time. So if I bring water to the triple point, which is at 0.01 degrees Celsius and 0.006 atmospheres of pressure, what will happen is the water will be a liquid and a gas and a solid all at once, and it will be changing, like boiling, evaporating, condensing, sublimating, like all of those things are happening at the exact same time. It's pretty crazy to see. But we can see like the normal freezing point, which is also called the melting point, is happening at 1 atmosphere, and this is at 0 degrees Celsius. And we see again at 1 atmosphere, the boiling point is 100 degrees Celsius. So all I'm doing with this phase diagram is basically just seeing what pressures and temperatures impact the phases of this particular piece of matter. So depending on the material you're looking at, your phase diagram might shift a little bit because the melting and boiling points will be slightly different. So one other thing I want to bring up before we get too far invested is what the difference is between boiling and evaporation. So boiling is when you're having that liquid go into a gaseous phase, but evaporation is only happening at the surface level. So I'll show you what this looks like at the next picture, but boiling is happening throughout. Evaporation is only at the surface. So only time you can have boiling occur where it's boiling throughout, you're having that change happening throughout an entire sample, is only at that specific temperature and pressure. Evaporation happens all the time. So here's a really good image to kind of show you the difference between the two. So on the left side, this is what is happening with evaporation. You just have those surface molecules changing from liquid to a gas. In the case of boiling, it is happening throughout. So all of it is occurring. In evaporation, your vapor pressure is going to be less than atmospheric pressure. So we won't see bubbles happening in evaporation because those pressures are different. In the case of boiling, the vapor pressure is the same as the atmospheric pressure. That's why we see those little bubbles forming all throughout the sample. And we'll see that occurring as we continue to expose it to that temperature and that pressure. So when I see something's boiling point, that is defined as the temperature at which the vapor pressure is equal to the standard pressure. So if I can change the atmospheric pressure I'm at depending on my altitude, that's going to change my boiling point. So if I, let's say, look at this graph here, at a typical altitude of 0, right, which is at sea level, the boiling point is 212 degrees Fahrenheit or 100 degrees Celsius. But let's say I were to go up in the atmosphere, maybe 5,000 feet, so going up in altitude, my boiling point will reduce now to maybe like 204 degrees Fahrenheit, which might be something like 97 degrees Celsius. So what we'll see is as we change that pressure, that's going to impact how my water can boil. This is why if you ever go in a plane and you order hot coffee, they have to be really careful with how they produce it and how they make it because the water is going to boil differently at a high altitude in an airplane. So boiling, again, will occur when the vapor pressure is going to be equal to the standard pressure. So when those two are equal, and that is going to change the boiling point based on the location you are on Earth. So at this point, you should know the phase changes. So think back to that early slide that we had and all of those arrows that we drew in. You should be able to identify which are endothermic and which are exothermic, so which absorb heat and which release heat. What's the difference between these two? And then how are evaporation and boiling different from one another?